Hello students, in the course of physics of linear and nonlinear optical waveguide. Today we have lecture number 37, and in the last class we started a very important concept, couple mode theory, very important theory. So we will going to continue the calculation that we started in the last class. So if you remember, in the last class we had an equation in our hand. So let me write down this equation once again, that A k0 square delta n square psi 1 plus b e to the power of I delta b z k0 square delta n2 square psi 2 plus 2I beta 1 del z a psi 1 plus beta 2 del z b psi 2 into e to the power of I delta beta z bracket close is equal to 0. That was the equation, where delta beta was beta 2 minus beta 1 and delta nj square is n square minus nj square, j is 1 and 2. Well, now let me write this equation as a equation. So in the last class I had a node here. So in the last class I wrote this equation, 1 and 2 equation was named. So let me write this equation as equation 3. So now what I do, equation 3 I will going to multiply a term like psi 1 star dx dy. I will going to multiply this psi 1 star dx dy to the entire equation. So sorry, equation 3 into this term. Okay, let me erase this. So equation 3, whatever the equation I have, and then multiply with this term. If I do, then I have a k0 square integration psi 1 delta n1 square psi 1 star dx dy plus b k0 square e to the power of I delta beta z integration, this is over some surface psi 2 delta n square psi 1 star dx dy. So you can see, by integrating this I am basically making some sort of coupling between the psi 1 and psi 2. Here I can have the first, this is the self coupling kind of term, this is the cross coupling kind of term. So I am making some kind of coupling here, plus 2I then beta 1 del a del z, then integration of mod of psi 1 square dx dy. Here I have this term n1 square, here I have this term delta n2 square. So, this term is now taken care. Now, here when I integrate this integration, here I have psi 1 and psi 2. So, one integration should be mod of psi 1 square and another integration will be beta 2 del b del z. With the beta term I always have the phase, this phase, and then integrate as psi 1 star psi 2 dx dy. This I have, which is equal to 0. Now, as I mentioned, I have some sort of coupling term here, and this is some kind of overlapping term. Overlapping term. This is the self overlapping, and this is the cross overlapping. So, normally what happened that this self overlapping term, which is overlapping between the same psi with itself, psi 1 mod square dx dy, is much greater than the cross overlapping term psi 1 star psi 2 dx dy. One can qualitatively understand that fact that if I have a field like this, say this is my psi 1, and if I have a field like this, say this is my psi 2, this is my psi 1. So, the self overlapping means I am overlapping psi 1 over psi 1. So, the overlapping factor is very high, but when I have a cross overlapping, so only this term which is overlapping, so only this portion which is overlapping, suppose I draw a field like this. So, this is the portion which is overlapping, this is the cross overlapping. So, this integral will be much smaller compared to the self coupling term. So, I can neglect this term safely. So, if I do, and if I define something more, which is say kappa 1 1, I define this as k 0 square divided by 2 beta 1, then integral psi 1 delta n square, because this term I already have in my equation, dx dy divided by this self overlapping term mod of psi 1 square dx dy. So, in the equation I have this term. So, I will going to neglect this term, and then I divide the entire equation with this term, this integral. Here and here this term will come, and also I divide everything with 2 beta 1. So, I can have a term like this. Also I can have another term say kappa 1 2 as this. Which is psi 2 delta n 1 delta n 2 square psi 1 star dx dy divided by the usual self coupling term over some surface. So, dx dy is the cross surface area of the this cross surface area of this waveguide, whatever the waveguide structure. So, we have a waveguide structure like this. So, I am talking about. So, this area, whatever the area we have, is basically my xy. Along this direction it is my z. Well, after having this kappa 1 and kappa 2, my differential equation become much more, whatever the equation we have here is much more simpler, and the simpler form I can have is this kappa 1 1 after defining that a, which is a function of z, then kappa 1 2 beta z, then e to the power of I delta beta z is equal to minus of I dA dz. So, I simplified it more, and eventually I have a very interesting equation which I wanted to find, and this equation is the evolution of the amplitude over z is equal to I kappa 1 1 a plus I kappa 1 2 b e to the power of I delta b z. So, I have a differential equation of the evolution of the amplitude A z, and this equation I figure out by integrating, by putting a very important step here. I like to recall this step, that I have an equation 3, and this equation 3, then I multiply this equation 3 with psi 1 star dx dy, and I am getting this equation, whatever the equation is now written here. Now, you can do the similar way. Similarly, I have equation 3, and I am going to multiply this equation with this term psi 2 star dx dy, that I can do, this is my choice. And if I do that and do all the procedure, follow all the procedure that has been done so far for A, I can end up with this equation, a similar kind of equation, and I am writing this equation here. This is a differential equation for the another amplitude b. How the b will going to change, it is given here. Note it, in the first case I have delta b, but in this case I have minus of delta b, because my delta beta rather is defined as beta 2 minus beta 1. So, in the first case I have a term beta 2 minus beta 1, and in the next case if you do the calculation rigorously, you will find you will have beta 1 minus beta 2. So, in order to make this beta 2 minus beta 1, I need to put a negative sign. So, that is why this negative sign will be here. So, now I have two very important equation, and this equation I write it as equation 4a and equation 4b. These are the coupled equation, mind it. Sorry, this will be 4b. So, the variation of the A will depend on B, and the variation of B will depend on A through this coupling term, So, first case I have a coupling term here, and in the second case I have a coupling term here, but still I am having one term like this. So, this is some term which I can also identify. So, kappa 1 and kappa 2 is essentially, so let me write down kappa 1 1 and kappa 2 2 represents the correction of the propagation constant of each individual mode due to the presence of other waveguide. So, what was that? So, initially suppose I have one waveguide and I have a propagation constant beta here. Then I have another waveguide, individual another waveguide, and this is beta 2. Now, what happened that I have both the waveguides. Sorry, let me draw in a logical way. Now, instead of having one waveguide, I am having both waveguide together. So, now this beta 1 and beta 2 will going to change because of the presence of this waveguide, and that change, this correction is given here. So, if I have a corrected term, say beta 1 prime and beta 2 prime. So, beta 1 and beta 2 prime now be corrected. So, beta 1 prime should be beta 1 plus some correction, and this correction say k 1 1 kappa 1 1, and beta 2 prime should be beta 2 plus some correction say kappa 2 2. That correction here we can we are talking about. So, now after having this concept, I can write my Az, since I know this is a correction term, I can write my Az as a new notation with e to the power of, because I know this is a correction. So, I can write these as a propagation constant like this, and Bz, the amplitude term, is also having a contribution of the correction as this. So, now A and B, which was initially amplitude, is associated with the phase term, and this phase is basically the correction in the propagation constant, that is all. So, here I can have dA dz is equal to del z say plus I kappa 1 1 a e to the power of I kappa 1 1 z, and so and dB dz will be simply in a similar way. I can write I kappa 2 2 bz, because this is, if I write, so it should be I kappa 1 1 a to the power I k z. So, I kappa 1 1 z, I can write it as a, and then the rest of the term plus say dA dz e to the power of I kappa 1 1 z, like that, and B I can write also in this way. So, I can put this and eventually I can put this here in this equation, whatever the equation I have, and if I put this equation, these two in these two equation 4a and 4b. So let us write it as 5a and 5b. So using four AB and 5 AB, we can have something like dA dz e to the power of I kappa 1 1 z is equal to I kappa 1 2. Then B, I can write this B as say okay, let me write the total term, then I will. So, it should be B e to the power of I delta beta z, it was original in the equation. This thing is, so dA dz e to the power I kappa 1 1 z is I kappa 1 2. B I can write as small b e to the power of I kappa 2 2 z into e to the power of I delta beta z. So, eventually I can have dA dz is equal to I of kappa 1 2 bz e to the power of I kappa 2 2 minus it is kappa not k. So, kappa 2 2 minus kappa 1 1 z plus delta beta z. In the similar way, exactly in the similar way, one can have dB dz is equal to I kappa 2 1 az e to the power of minus of I kappa 2 2 minus kappa 1 1 z minus delta beta z. Now, we can define, because we know that kappa 1 1 and kappa 2 2 as the modification of the propagation constant delta, propagation constant beta. So, I can have beta tilde in general as say beta 2 prime minus beta 1 prime, which is delta beta plus kappa 2 2 minus kappa 1 1. Beta 2 prime and beta 1 prime I have already defined here, and if you put, you can find that beta 2 minus beta 2 prime minus beta 1 prime is delta beta, because delta beta initially defined as beta 2 minus beta 1. So, eventually I have a equation which is having the form like dA dz, which is a pure amplitude term, is equal to, is evolving following this differential equation. Then B e to the power of I delta beta tilde z, and this is one equation. So, let me put in a bracket. Say equation 6a, and another equation for B I have say 2 1 a e to the power of I delta beta tilde z. So, this is equation 6b. So, these two are coupled differential equation and we almost there. So, these are the coupled differential equation. Of the amplitude of the modes. So, this is a coupled differential equation of the amplitude of the mode. So, that means this is my waveguide structure I am drawing once again, and suppose in the 3D it is like that. So, I have a wave here launched somewhere having some kind of mode structure, and during the propagation this is along z direction, it will going to propagate. So, this is z direction. So, this is the amplitude I am talking about, which is a function of z, and this amplitude will going to change over the distance z. So, this is the distance z. So, what happened that it will going to change, and there is a possibility that some of the energy can pass from this waveguide to this one, and at certain distance I can have a field structure like this here. My drawing is bad here, so let me erase this. So, I can have some field, some energy at some distance here. So, I can have some energy say here during the propagation. Initially, I do not have anything here in waveguide. So, this is waveguide 1 and this is waveguide 2, WG1, waveguide 1 and WG2, and gradually it will going to change, and I will have something here at some point, say at z equal to some distance, say LC. This is z equal to 0. So, how this amplitude will going to change over the distance, that one can find out by solving these two differential equation that we derive here. These two very important differential equation. So, in the next class, today I do not have the time to solve this coupled differential equation. So, in the next class we will going to solve this coupled differential equation, and then we have an idea that how the field is going from one waveguide to another waveguide. So, with this note I would like to conclude my class. So, thank you for your attention and see you in the next class for the rest of the calculations. Thank you.